Hello everyone. Thank you for attending this next forum. I'm Stephen Coates, General Manager for GaN Systems here in Asia. Today I'll share with you how GaN has really reached its tipping point and how we at GaN Systems are transforming the world. We're transforming the world with smaller, more efficient, more reliable, and more cost-effective power electronics. Our industry is poised at the beginning of what may well be the most significant revolution in electric power since electricity was first used to light a block of New York City 150 years ago. Global electricity demand has grown by nearly 33% over the past decade, and it's expected to grow by another 50% by 2050. And at that same time, renewable energy will account for nearly half of global power generation. So it's true to say that power and power electronics really are at the center of our world. And here are the three megatrends that are driving a real revolution in today's power electronics. The first megatrend, the digital economy. The world has turned more digital. Digital equates to data. Data equates to data crunching, data storage, data transmission, and all of that requires and means more power. This growth of data has resulted in significant needs for data centers and 5G. And this infrastructure requires more efficient and smaller sized power electronics. The second megatrend, electrification. So many devices that were not electric before are now being electrified. Best illustrated by the picture in the center, the electric vehicle. But there are many other examples too. IoT is another example where we're putting sensors everywhere, and sensors need power. And security cameras and cell phone base stations and many others. This drive for electrification is driving the need for efficient power electronics. And the third megatrend, energy efficiency. Carbon dioxide reduction and energy efficiency are truly driving clean energy. And those systems use lots of power electronics. So three megatrends, all with the need for power electronics that use less energy and use less materials to get the job done. So let's review some of the major contributors and activities in our digital economy. So do you have a minute? We very often think about that phrase and what happens, in a 60-minute time period. Let me tell you about some of the things that happen in that minute. By the time I finish this slide, the world will have changed subtly, but irrevocably. 267 babies born worldwide, 2 auto thefts committed in the USA, 116 people will get married around the globe. And that's just in the real world. Now let's look at what happens on the internet in that same 1 minute period. So 4.5 billion users on the internet, 66,000 photos shared on Instagram, 510 comments posted, 293,000 statuses updated, 240,000 photos uploaded every minute on Facebook. 97,000 hours of content are consumed by Netflix every minute. So a lot happens in a 60-minute time period. And things get bigger and bigger. Data and hence power is skyrocketing in many different segments. Let's just take a look at a few. First is the Internet of Things, where the world is putting sensors everywhere and systems to take action on that data. So today, it's 20 zettabytes of data. By 2025, that's a 4x increase to 73 zettabytes. And you can see at the bottom, that's an awful lot of gigabytes. So lots and lots of activity in the Internet of Things world. And AI, artificial intelligence. AI applications, AI algorithms are used in many areas to transform the way that people live, work, and play. It's key to note the insight from Sanjay that these types of applications require 6 times more DRAM, 6 times more memory than traditional workloads. And that extra memory requirement means more racks of equipment in the data center. And as you'll see with GaN, smaller power electronics so that that memory can fit into the freed up space. Another market segment adding to skyrocketing data is the autonomous vehicle. It's estimated that autonomous vehicles will generate 4 terabytes of data per day from their onboard cameras, their radar, their sonar, their GPS, and their LiDAR systems. If only 10% of today's users adopted self-driving vehicles, that would generate 40 zettabytes of data annual. So the autonomous vehicle, another huge source of growing data. So electrification, we touched on this earlier. Nearly everything we touch, everything we use, everything we read requires power. And the number of devices is rapidly increasing. We can all look at this picture of gadgets and we recognize many that we own and use. And there's many more to add, like e-bikes and e-scooters. And as you see on the right-hand side of this slide, that forecasted growth of electronics is fast, up to 5x growth over the next 3 to 4 years. Augmented reality, virtual reality, both skyrocketing. Everything requires lots of data, and lots of devices mean lots of power is required. Adding to the electrification list, of course, is the electric vehicle. Volumes are forecast to grow very significantly, 30x over the next 20 years. Growth rates more than typical of consumer devices rather than cars. And that leads to huge semiconductor market growth. And EV growth reduces dependence on fossil fuels, reduces carbon dioxide emissions, reduces greenhouse gases, but it increases global electricity demand by 30%. So we've got to make sure that power electronics are smaller, lightweight, and they've got to be super efficient. Now, let's take a look at how the digital economy and electrification are impacting global demand for electricity, how renewables are a part, and what industry is doing, what we're all doing to support these initiatives. Reflecting back on the third megatrend that I mentioned, energy efficiency, the good news is that renewable sources will climb to 40% of demand, resulting in global CO2 reduction supported by regulatory requirements and strong consumer demand for sustainability. Now, the not so good news is that 60% of electricity still remains fossil fuel. Let's look at why this is so important. Unfortunately, the world experienced a global pandemic that required a worldwide lockdown. The COVID-19 lockdown affected us all, but it did give us the opportunity to see real-time the impact that we're all having on the environment. And it's clear from these images that we have a challenge and a true responsibility to make things better for us and, of course, for our future generations to come. To boost energy efficiency and make the planet healthier, companies and governments are all stepping in. In the data center area, government recognizes that energy, its supply and demand, are strategic to national economics and, of course, to security. So they have set rules, they have set targets, and they have clear plans to increase efficiency of the data center and the equipment that's used in that data center. In automotive, companies have been under regional governmental regulation for some time, and they recognize that electrification must be a major part of that strategy. And in the consumer area, We all like to get our Amazon deliveries. Even here in Taiwan, I look forward to my Amazon deliveries. But most of those trucks emit CO2. Then there are all of the warehouses that need to be lit up and powered and cooled. The robots to do the picking and the packing, along with computers, all consuming power. Fortunately, some of the big players are taking their own action, as is shown on this slide. So on the surface, all of this data and electrification, of course it looks great, but we all have to do our part in reduction of energy loss, our part in a reduction of materials used, our part on a reduction of cost, or we could end up in a very dark and dreary place. And that's why we're here today, to talk about the mighty power transistor and its important place, its primary place in the efficiency equation. This is a key chart. In the power world, the transistor is the critical component. I think most of us know this. We live it day by day. But importantly, it's our job to make sure the world knows it. First, the panel on the left. Power electronics is ubiquitous. There are power sources and power users. And always in the middle is the power electronics equipment. This can be as simple as a travel charger for your cell phone, or as complex as the electronics in an EV. Second, in the middle, there are universal needs for all power systems. Higher efficiency, so we don't waste the power as heat. Smaller size and lighter weight, so that we fundamentally use less materials. That lowers the system cost. We've all become used to our electronics delivering more for lower price with each generation. And of course, we all demand the highest reliability. Not as important in the digital world, where if your cell phone breaks, you can just get a new one. When a power system breaks, they have to work for years. They have to work for decades. They have to be safe. They have to be highly reliable, and reliability is paramount. So third, on the right, transistors are the key to achieving the objectives I mentioned in the middle of this slide. Many well-respected people have called the transistor the most important innovation of the 20th century. It was important enough that its inventors were awarded the Nobel Prize. So the bottom line, the power transistor is the most important component, the most important semiconductor in the entire system. So having the best power transistor is absolutely critical. So, having established that the transistor is key, let's look at where the silicon world has taken us today. And then, how do we move forward? The RSP versus voltage chart here illustrates that silicon has reached its maximum performance. As shown on the chart, 2D silicon designs have reached their limit. 3D designs have even slightly exceeded the 2D theoretical limit, but also asymptotically reaching their limit. And as we've discussed previously, the world is not stopping in its demand for smaller, lighter, more efficient power electronics. So industry has shifted to technology that has the ability to continue along the continuous performance improvement track. GaN's already dramatically exceeded the performance of 3D silicon, exceeded the performance of silicon carbide, and that is today. And GaN's very, very far from its theoretical limit. And we'll see those devices in years to come. In GaN systems, we've already reduced the RSP of our first generation by a factor of 2 in our second generation devices. Wide bandgap is here, and it's here to stay. Market requirements and GaN supplier readiness now make the time right for GaN. On the left, the graphic shows how GaN, silicon carbide, and silicon compare in some of their fundamental dimensions. As you can see, GaN outperforms both silicon and silicon carbide in these fundamental properties. The biggest differentiator for GaN is that it switches extremely fast. And what results is significant value for our customers, which is shown on the right. So efficiency, 4 times reduction of power losses. Size, 4 times reduction of size and weight. And lower cost. So why lower cost? Well, electronics that are smaller, they use less copper. They use less aluminum. They use less plastics. Electronics that are more efficient can be smaller or even have no cooling systems. And all of this reduces bill of material cost. The transition to GaN from silicon, it's not a unique shift in power electronics. Power transistors have been around since they were first introduced in the 50s. And this slide shows that evolution. Today, market needs are primarily addressed by silicon MOSFETs and silicon IGBTs. Silicon carbide and GaN are the new materials disrupting the market. Just like when MOSFET and IGBT took over the lion's share of the market in the 1990s, for silicon carbide, this means being very high voltage, very high power alternative for silicon. And for GaN, this means being the most cost-effective mass market alternative for silicon. We'll look at these markets in upcoming slides. But first, why now? Why is this the tipping point? So 2 factors really have made GaN adoption tip. First, the technology. We made our GaN devices more reliable than silicon carbide, just as reliable as the best silicon. And reliability is key for all markets, but especially high rel, industrial and automotive. GaN systems parts are in space. We're racing in Formula E race cars. We're getting the job done in really exacting applications like factory motors. These are the most challenging environments for power transistors. GaN parts are proven in the field. In addition, product volumes up, costs are down. The last 3 decades of semiconductor manufacturing experience has shown that as volume increases, economies of scale kick in, learning curves kick in, and costs go down, and GaN's no different. For GaN systems, our 2nd generation parts are smaller, they're lower cost. Prices have been cut in half for some of our most popular parts, which results in increased demand. So GaN parts have now achieved lower prices than their silicon counterparts. Secondly, the industry megatrends. We touched on this earlier. These have been extremely favorable, I think. End markets are pulling for higher efficiency power to be the greater differentiation. For example, automotive OEMs want faster charging. They want to reduce the number of batteries. Many OEMs are fully committed now to going fully electric. Companies like VW, GM, Ford. Consumer charger OEMs are looking to make smaller power supplies that charge batteries faster. And data center customers want to pack more computing in a given space to increase revenues in their data center. So in summary, that's why power electronics is important. That's why GaN's important. And that's why we're really at this tipping point. And the analysts agree. It's truly exciting to be part of an industry that's forecasted to grow from 0 to $1 billion within a decade. With GaN power system companies making very different products across many applications, they'll all take advantage of GaN to meet their sustainability targets, as well as providing the products that we all want to purchase and use. Let me show you some of these products and the value they deliver. Today, GaN is used extensively in 5 market segments, from lower power consumer GaN chargers to very high power EV, and every market in between. GaN's in space, GaN's in Formula E race cars, GaN's in consumer, it's in automotive, it's in data center, 5G, it's in industrial, and it's in renewables. As we wear, carry, hold, and ride with more electronics, none of us want to carry an equivalent number of chargers. Fortunately, the vision of USB has branched out beyond keyboards and mice, and now consumers want fewer, smaller, faster chargers. And the market's responded with GaN chargers. Here's some highlights of what's changed in the charger and the adapter markets. On the left side, you see chargers for mobile phones and laptops where efficiencies have increased and sizes have shrunk by 2x. On the right side, you see how adapters for larger laptop and gaming PCs have increased in efficiency and decreased in size, a 3x size reduction. Taking the vision of consumer devices one step further, think about a world without charging wires at all. I think we would all love that, where wireless charging delivered in an easy way really becomes a reality. Today there is wireless charging available, but it's really not precisely what we want or what we need. Exact positioning, low power, a small jostle and the charging stops. WPT1, the first incarnation, it just doesn't meet our wants and needs. WPT2, with its positional freedom in X, Y, and Z planes, easily achieves higher power for fast charge. Its ability to charge several devices at once, and no interference from metal objects. This becomes the ideal solution. Let me show you some of the ways companies are using GaN in WPT2. Here we see applications from 30 watts to 1 kilowatt. Surface charging for gaps of up to 200 millimeters, that's 8 inches. Charging 1, 2, or 3 devices simultaneously. The enabler here is GaN, switching at megahertz frequency, providing optimum efficiency and use case flexibility. Moving from consumer to automotive, let's take a look at the applications for GaN in an electric vehicle. There are 8 common applications: in audio, in the traction inverter, in the DC to DC converter, wireless phone charging, 48-volt mild hybrid, onboard charging, LiDAR sensors, and wireless battery charging. And the most important power electronic systems in EVs are the chargers and the inverters. Here's an onboard charger, what one of our customers has done with our GaN. So they built 4 different versions of the same charger, one in silicon carbide, and 2 in GaN. And what turned out to be the case is that the GaN systems design outperformed everyone. We were 5 times smaller than the best silicon, and we were 3 times lower losses than the best silicon. And here's an inverter. Another of our customers has publicly shown the cost breakdown of their old silicon inverter versus their new GaN inverter. The cost breakdown shown on the right. The new GaN inverter versus the old silicon inverter. Almost 2x power density improvement, and that's critical. As everyone, all of the OEMs, they want to use more of that space in the car, fewer batteries, longer range. Plus there's an 8% cost reduction. And on the left, the all-GaN car made by Toyota. These prototype cars use GaN systems GaN. They use GaN in the traction inverter, they use our GaN in the onboard charger, and they use our GaN in the DC to DC. So switching markets, let's look at data center. We touched on this earlier. Innovation across all electronics markets is requiring more computing. It requires more data, more and larger data centers. The 53 zettabytes of data for IoT devices, that requires an additional 500 million servers in 5,000 massive data centers. The 40 zettabytes of data for autonomous vehicles, that's another 400 million servers in 4,000 massive data centers. The growth in AI, machine learning, voice and image recognition will simply add more and more, all of which is rapidly driving up our consumption in energy, data center OpEx, data center CapEx, and if not carefully planned, a very significant increase in carbon footprint. And as all of the major components in the IT equipment will consume more power, the CPU microprocessor uses more power, the graphics chips use more power, and the memory uses more power. We've got to think about supplying that power with smaller, lighter, more efficient power supplies. In the average data center, approximately 22% of power is wasted as it travels through the multiple power conversions necessary to go from the electrical grid to the microprocessor in an individual server. Energy efficiency and density can be gained in three areas. Number one, in the UPS. Here, high voltage is converted and brought into the building. Here I show a large centralized unit, but the evolution is underway to make smaller decentralized units for risk mitigation. Number two, in the rack power supply, at the server rack where AC is converted to DC. And lastly, the individual server power supplies, where the DC is converted to low voltage DC on the server board. GaN solves three design challenges. Increased efficiency. We reduce the creation of heat by being more efficient, with a corresponding reduction in electricity costs. Reduced emissions. Every efficiency percentage point that we gain reduces the need for power, which lessens the environmental impact and reduces carbon emissions. And reduced size. More real estate to add more CPU and more memory components. In data centers, it's very interesting how small size and high efficiency translate to value. The number one expense in a data center is the power to run the servers. So decreasing the power losses reduces the OpEx. But power density is more important because it affects revenue and profit. The picture in the lower right shows a standard power supply form factor. The GaN version is 1.5x better power density. Now look at the server racks. With less space needed for the PSU, more servers can be put into the rack. More servers mean more terabytes per rack, and that means more revenue per rack. We recently did a calculation with a mega data center operator, and it comes out to be $3 million per year per 10 server racks. And the resulting dollar impact is big. Let's look at the numbers. For a big mega data center operator, it's $3 million revenue increase per year per 10 server racks. That's 100 metric tons of reduced CO2 emissions, and it's a $13,000 reduction in OpEx. For all major categories of data center, from enterprise to multi-tenant to hyperscale, hardware energy efficiency and hardware power density are truly important, and they're an important part of the executive business strategy. Data centers have been pushing the envelope in many areas of power efficiencies and density, but now need to add hardware as a driver to both their economic and their sustainability profile. And as every company becomes a data company, both enterprise data center and customers of multi-tenant, we all need to rethink the relationship and make it a core business decision area, not an afterthought. It's time to play catch-up. It's time to abandon 10-year-old practices and equipment so that the enterprise data center no longer looks like this and is managed like an old server closet. And industrial. 45% of the world's energy usage is for industry. 2/3 of industrial energy usage is for motors. So 30% of the world's energy is used by motors, and they're everywhere. And GaN's helping to reduce their impact on the environment. Here's a nice write-up on the Siemens website describing their new microdrive. Beyond the typical advantages that GaN enables, Siemens innovation identified additional benefits: faster motor response time, increased motor lifetime, lower system costs because of reduced noise suppression when using GaN. And last but certainly not least, renewable energy. GaN directly impacts renewable energy at its creation and distribution. Here you see a typical solar and battery storage installation. And here you see the economic benefits: 4% increase in revenue, 8% reduction in cost, 12% increase in profits, and the system's 30% smaller with that consummate reduction in materials. So I guess it probably is a question that you can have your cake and you can eat it too. So tying everything together, in our world of more data, in our world of more electronics, the need for clean energy and reduced CO2, We must be more frugal with our materials. We must be more frugal with our energy. And we must be more frugal with our money. The existing legacy silicon has run out of gas. GaN's here today. It's proven value. It's proven reliability. It's proven with customers. It's proven in the field. Now is the time for wide bandgap. Now is the time of GaN. And thank you for your time. Once again, I'm Stephen Coates. I'm General Manager for GaN Systems here in Asia, and I'd be happy to answer questions later. Thank you.